student better. She was like,
She did some research.
That's what I put. So hopefully.
I did it like one teaching about it back in, but then I lost it.
Through, like,
Got me about a year.
I think it's like through
She
like.
was like, what makes sense?
The first one was like, which is not a rule for handling chemicals, and like they have all songs of like rules to handle chemicals, and I was like, I don't know what the answer is.
Wear gloves, apparently.
That was yeah. I think I got it wrong, which is
One is, I think Steve had like a trip up in the words, like made it wrong.
yeah. I definitely did not put C, so I'm not really upset about it because like I think it's
So no problems with the homework. You can just, you already submitted the videos and you can just copy paste a couple of images into whatever Word or PowerPoint.
Can you read number 2? What does it say?
But this is not for the coming Monday.
No, I know, but just for like.
You torture me. I cannot read my own handwriting. Select 4 sets of Lx, Ly, Lz parameters with which would represent different dimensionality of confinement 3D, 2D, 1D, 0D. We didn't cover this yet in class, but just giving you a heads up.
Okay.
We will go big above one-dimensional space and go to like 2-dimensional, 3-dimensional. So, okay, probably there is no time for too much chatting. Steven, is the camera focusing on the board?
Yes, I can see the board.
Okay, good. So here is the space of theories that we browse in. And we look at evolution operator, Schrödinger, time-dependent, time-independent, Heisenberg, and today we will start a new concept of so-called density methods. Because it's boring to use the same tools all the time, right? And we covered free space. Now we are going for one-dimensional box. This is things that some of you may remember in the middle of the night. Maybe not. I think this is just a glitch. The recording comes from this one. So you do not need to make smart faces. So what did we cover last time? The zero between 0 and L, infinitely everywhere else. Kinetic energy, second derivative, potential energy 0 or infinity. And then for time-independent Schrödinger equation, when it sets up boundary condition, we function at boundaries equal 0, right? Keep sleeping, relaxing. I'll tell where to wake up. There will be something important to focus on. And we assume the solution in form of coinciding plane waves that run into each other with coefficients C plus C minus. We found that and through Euler equation, we are looking at solution in the form of sine and cosine with some coefficients. If we do all math carefully based on your homework number X, problem Z, whatever, 3.5, one can find that solution has this form, discrete rate in front of independent variable and normalization constant 1 over square root of the length. And on the language of coinciding plane waves, it will come as C plus and C minus are equal by value but opposite by sign, and they both are imaginary. But if doing everything carefully, one is getting the answer that you were deriving yourself, or you can find it in any book. Good. Do not leave, do not leave. I decided to use 2 lectures in one. So, here is the verbal formula for the things that we will accomplish. I just see that I don't block it. For the thing that we are going to accomplish. For about 2 meetings, today and Monday for sure, maybe longer, we will try to recognize what you have done in the lab on Wednesday. So it was like a couple of lines of programming, not very complicated to run and observe, but to recognize it in lecture material, we need substantial amount of time. And I already remember from talking to you that you were posing deep questions, trying to understand what is going on. So it is very untrivial, although simple in implementation. So we are trying to prepare transitional state. In real life, you get it all the time when, for example, if you excite system from ground to excited, but you're not done. You're halfway of exciting. So it's neither here, neither there. So we have superposition between ground and excited. And then, since it is neither wave function is not ground, not excited, so it's not in eigenstate. It is expected that it will change in time. And since we try to predict future, we are trying to catch how will it change in time. Right? So later on, we will try to predict expectation values of some simple observables. But right now, we just want to interpret and look onto the probability distribution. Where is the electron at different slices of time? In the lab, you already got it, and you send some or bring some homeworks with maybe some minimalistic reports, what you see in the numerical form. But now we will try to reproduce the same result with pen and paper, or whatever, finger and touch screen. So we will try to write an equation for distribution in space, for probability distribution. And it will include the summation of terms, and each term will contain factor that depends on time and factor that depends on position. And we will just look what they are, where they are coming from. You do not need me. Your experience and education is sufficient to do everything yourself. But let's just do it quick, easy way, and jump to next chapters sooner. So a little note that is not needed, but if you decide to read some books in quantum theory, or if you just look into Wikipedia, you will always very frequently see, if you want to cover this particle in the box from some text, you will see an image that is so frequent that no one typically catches a little inconsistency. So there is an image that tries to mix apples and oranges in the following sense. One draws a potential surface, potential energy, and draws probability distribution. So on x-axis it is position, but on the y-axis it is ambiguous. On one hand it is energy, on another hand it is probability. And one adds energy and probability, which is a little crazy. But it is very visual, and let's just quickly look at that. So those are your eigenfunctions, like first and second things. And now we are not making an offset from zero, right? But you already do know the energies. So it's number of the solution squared divided by size squared. There are some constant mass. So if you take this away as a constant, it will be just n squared. 1, 4, higher up. And if you want to match together, so I'm already doing it here, naturally, but it is a little corrupt logic. So you make an offset for energy levels according to their energy, and on the same new axis, you immediately draw a wave function or probability distribution. So just do not feel confused if you are very careful about strict logic. It's just common practice. And people do either probability amplitude, the wave function, or probability distribution, which will be like square of sine and square. So energies are 1 and 4 is the rest of the factors. And it is what it's been sorted. Okay. Now, we are going to explore transition state. We are allowed to add together general solutions to build partial solutions, right? So why don't we add together the ground and first excited state? Wave function always must be normalized, which means upon we construct this wave function and find probability distribution and then integrate it, we should get 1. Because total number of electrons in our system is 1 that we can find with probability 1. And we know that this function is normalized and this function is normalized. If we simply add them together and then multiply and integrate, we should get something that will be bigger than 1, 4. Right? Not right. But we know that it is possible. The theorems allow us to do so. And there is just additional restriction for normalization. Therefore, if we match the coefficients, if we multiply each, suppose that we want to mix them in equal proportions, 50-50. But since wave function is always taken as absolute value squared, we need to put square root of 1/2 in front of each. And it is only one particular case which is also typical for textbooks, because 1 over square root of 2 is much simpler than like 1% and 99%. But the connection between these two things should be as follows. This 1 squared plus this 1 squared should give 1. But here you see that it fulfills 1/2 plus 1/2. You're very welcome to sit and relax and not to take notes. I'm serious, but be ready. The complexity will raise up, and at some point you may find that you are missing something. So just be careful. Stop me or make notes and just alert me. So adding together wave functions in Dirac notation and expansion coefficients. Their sum should be 1. How do we predict future? Typically by showing the time-dependent expansion over eigenstates. We do have eigenstates, we do have eigenenergies, and we do have initial coefficients. So we, in general problem, we find initial coefficients, but here we just postulate them for simplicity. So basically we can immediately construct the solution. So instead of writing summation sign, I'm putting stuff because there are only 2 terms in summation. So there are eigenfunctions. There are initial coefficients, 1 over square root 2, 1 over square root 2 here and there. And there is a time evolution, accumulation of phase with energy 1 of state 1, with energy 2 of state 2, right? So there is nothing but the way how we propagate the. Now let's look on it from a little bit different point of, a little bit different aspect. What if we combine this initial expansion coefficient and phase accumulation into time-dependent expansion coefficient? No one forbids us, it's possible, because absolute value square of imaginary exponential is 1. So if you multiply 1 over square root of 2 on this exponential and 1 square root 2 over another exponential, normalization will be fulfilled. Nothing wrong. But instead of, it's just a little tribute to laziness. Instead of writing these long things all the time, we can tell that it is same superposition of round and excited, and there are time-dependent expansion coefficients. Their absolute value stays the same, but they are appearing at different phases. And for the wave function, it doesn't matter, but if we are going to find either observable or probability distribution, the phases hidden into this phase accumulation will result in some effects that you already have seen in the lab. So let's look at the teaching that was offered to us by Yun at his last slide. If you multiply cat times bra, then product, then you convert vector into the matrix. So let's just do this operation algebraically without thinking of the meaning. Why don't we try this little mathematical experiment? So we take our wave function and conjugate wave function and multiply it in the form of cat times bra. So it will form the products of the wave functions, which will either coincide or not coincide, and products of the time-dependent factors. So in each term, the time-dependent factors will match the pattern of the spatial things. If two indices coincide here, two indices coincide there. If two indices do not coincide here, they do not coincide there. Right? So they are kind of echoing each other. But this part would correspond to either abstract state or spatial distribution. And this part, accumulation of phase, in a sense of something that is different from wave function. Wave function is always proportional to the first power of this coefficient, and here's the second power. Why? I'm torturing myself and maybe use this expression. Why we are writing so long? Why do we need second power of expansion coefficients? This second power of expansion coefficients or products of wave function came up in two things that we are interested in. First, in probability distributions, and second, in finding observables. And they are universal. Through building this product, we will get some benefits. They will be seen only maybe by Monday, end of Monday meeting. But the benefit that we will be able to identify some common terms that we can write down once and then use multiple times instead of repeating. Right now it looks like too many symbols without any reason, but there will be benefit. Yes?
Is that result then over 1 problem?
No, it is 2 by 2. I'll cover those quick notes, but I'll cover them. So generally, the object there is a advanced thing that now we can fall asleep and skip. But there is an advanced thing called either density matrix or density operator that is naturally connects wave function, distribution, and observables. And generally, this wave function and coordinate distribution should have different values of independent variable for Bryan curve. But if we want to look at the probability distribution, we plug in the same values of the independent variable here. And we are going from abstract density operator that if your goal is only this course, you can forget right next second, into probability distribution, which is just psi star and psi. So we are going from this abstract Bryan cat to the space distribution and time distribution. The arrangement of the terms is the same, right? So they are echoing each other, time-dependent part and spatial part. And coefficients here and there are coinciding: 1, 1, 1, 1, 1, 2, 1, 2. So if we are able to add together these 4 terms, then we will have probability distribution that was popping up on your screen during the lab without a computer. You can just predict it and write it at each point in time. Looks doable, right? I don't know, in modern world with computers, no one needs it, but suppose that suddenly we are on the inhabited island without computers, and for some reason we need to find time evolution of superpositional state of a particle in the box. So let's look a little further. So 4 terms: time factor, space factor, and we can plug in the actual values. For the space factor, we will just multiply this sign. Should be they coincide with both binaries over L because it is the same functions and they are conjugation. There is no imaginary part. And there is one more notation just to make number of symbols smaller. So this combination expansion coefficients can be referred to as rho 1, 1 instead of repeating that T1 bracket T over there. So just put here these two indices. So 4 elements of density matrix, and by assigning indices to them, run over different pairs of orbitals, you see that this information can be arranged in a square matrix. And right now we are doing it for the simple case of 2 by 2, but generally it can be for 1000 by 1000 or whatever. So we do have spatial factors, which are just products of the eigenfunctions, and we do have time-dependent factors. So let's look at them closely and make some observations. So for element 1, 1, we have evolution forward, first energy times T minus imaginary unit. Evolution backwards, same thing is minus 7. So plus and minus with the same pace. So 2 exponentials with e to the x times e to the minus x, you give 1, right? And since we have initial expansion coefficient stored in here, there will be 1 half. Clear what comes with? It's from like C1, C star, 1 times 0. So if you look to another element where indices coincide, so evolution forward with a pace defined by energy 2, evolution backwards with the same energy. They multiply to each other, compensate, and we have a constant. And for the elements where indices do not coincide, we have product of exponentials going forward in time and backwards in time with different energies, different eigenenergies. And when we combine them into one exponential, we can consider propagation forward in time with energy 1 minus energy 2, with some negative energy. And if we swap the indices, the sign would be opposite. So propagating forward in time with energy difference positive. Okay? So for this particular case, for specific case, we already have explicit values of this element. And practically, we just need to complete the summation and see what happens. What do we see, and which simplifications we can see on this path? The off-diagonal elements when indices do not coincide. Here is sine x sine 2x. Right? Here is sine x sine 2x. They are the same. Right? And here the accumulation of phase is the same as opposite direction. Right? So this one comes to here, this one comes to here. So the spatial part can be placed outside of the brackets, and these two things can be combined by Euler expression. Right? And then instead of imaginary exponentials, we will get something simple. We just discussed this. So going back to spatial part, you remember this figure from the left, right? So now you see it's, well, you saw it before. It's products of the basis functions. So the ground state function will be probability distribution this center. Then the excited state function is sine of 2x with 2 peaks, right? And if you multiply these two functions, no matter in which order, so there are technically two lines, orange and purple, but they coincide. And it will be a function that has negative part. Right? So when indices coincide, the function is distribution is positive. When it is, obviously, I know this word, transition density. So if you were running TDFT, deals with density, this is transition density. It can become negative. And now we need to add together all 4 terms, but each of them is.
Is there any reason we went from 2 over L to 1 over L?
Yes. If those are just basis functions, then it will be 1 over L. If you multiply them by the initial condition, then it will be factor 1/2. So we need to add together all 4 functions, but they will come with different. It's exactly what John was asking, with different percentage. And the percentage of the first and last will be 1/2. And percentage of the second and third will depend on time. Therefore, adding them together will be different. Results of adding together these functions will be different at each time step. And this is the reason why you see dynamics. So you add these same functions, but their relative proportions are changing. I hate text, but just move. So it's not all, but we are very close. So you already saw that we are dealing with exciting state. Our local goal is distribution in space, and the solution is summation of 4 terms, each of which is product of time-dependent factor and time-independent factor. Time-dependent factors can be referred to as elements of principal measures. I think if you start practically adding them together, you will be way over the limits. So I postponed it for Monday, but the idea is that we put the product of sin x and sin 2x over the brackets and add these 2 things together. Summation of opposite exponentials will come to the cosine of the order, right? Because the sine parts of each exponential will cancel. So that each term will determine the sense of diagonal term. This expression will be just cosine of energy difference times time multiplied by this function, which half of the period is positive, half of the period is negative. So basically, this was just a little introduction of what you already did in the lab. Okay. So when one adds together these 4 terms, each with its own factor, the probability distribution is not stationary. At some point of view, there is more probability to find it on the left. At other part of time, there is more probability to find it on the right. And on Monday, I'm going to offer you to get to this time-dependent thing through derivations rather than computing. Just to get the shapes of the function by trigonometry and seeing it more illustrated. So the probability to find electron from in this range of space will be equal to this error, right? So probability to find electron from x to x plus delta x. And if one adds together all probability, it should be 1. I think not for today. So we will not compare this stuff. I hope. Have a nice weekend. And I'll stay here if any questions. Yes, ma'am. Absolutely.
So in this example, there's actually 2 primary positions that probably might be. Is there ever an example where there would be, say, 3?
Oh yes. This is not the best example for visual representation. Best example will be if we excite several excited states, and if the potential will be different from rectangular. Then it will be maybe narrower peak, bumping into the wall, reflecting, going backwards, and it will be more continuous. It will be like single peak, just going forwards and backwards. But to get such nicer picture, one would need to add together larger number of crazy states.
Have a good weekend.
It's a-
It's for the charge station when you're. These are kind of related. It was definitely in that chapter.
It's funny because I worked with him, but we don't do a lot of analytics like research. And so I
Oh, it's
practice.
no, the class stays with the class. You know? That's
Like I remember more from second semester than first semester because I don't use the first semester stuff really ever.
What do you guys do research on then?
My project that I'm writing actually now is we were watching proteins folding under confinement.
Okay.
So we're kind of doing artificial monthly chaperones.
Oh, that is not what I anticipated him doing at all.
He does a lot though. Like Dr. Todd is doing a whole lot with organic frameworks, size manipulation and stuff. We did carbon nanotubes, foil nanorods, and graphene oxide last year. And then I still have the file. There. They're doing something with graphene oxide. Yeah, it's a good time. It's a lot going on, so there's always new projects and information.
That's what happens when you have more than 2 graduate students, huh?
Well, he has just 2. 2 graduates, yeah. We lost one because she got a job. Thank you.
Thank you.
Hi.
So, 2 graduates, I was working
She
on
didn't
it.
graduate? Well, she can have